Alright, so we're in for a bit of a smaller video today, and essentially what we're doing is we are basically comparing a couple of acids, and we're going to do a little bit of calculations at the end. Alright, so our comparison of weak and strong acids. Basically, for weak acids, HA, which we'll show in our thing in a minute, is defined as stronger than HB if, okay, so this one here, acid HA, is stronger than this acid if its equilibrium lies further to the right. Okay, so there's our equilibrium. If this lies further to the right than this, we can say that this acid here is the strong acid. So the relative strength of hydrochloric, citric, and acetic acid are as follows. Hydrochloric acid, no surprise, super strong. Citric acid is weak. Acetic acid is weaker still. Now, basically, the degree of ionization in hydrochloric, citric, and acetic acids are as follows. So, strong, weak, weaker. You can probably guess which way this is going to go. Basically, HCl 100% ionized. Okay, so its equilibrium is right over to the right. And if this is acetic acid, its equilibrium is a fair bit over to the left. Citric acid is about 8.6% ionized in solution, and acetic acid is about 1.3%. Now remember, the amount of ionization, so the equilibrium of this, is dependent upon temperature. Okay, it's one of those things. So the equilibrium, or the equilibrium constant, which is the same as the ionization constant, is, well, it's not, but the same sort of concept, is dependent upon temperature. And here we can see it. So these are all at equal concentrations. Okay, 0.1, 0.1, 0.1, and we can see the difference in their pHs. Okay, so their pHs are different, and that's because the different degree of ionization. All right, so equilibrium of ionization. Let's bring these two concepts together. Basic strong acids, there is no equilibrium. It shoots straight over to the other side. It's all done. So hydrochloric acid will not form as an equilibrium, which was why we give it this arrow here. And remember, we're now including the water, and we're including the hydronium ion. Now, a weak acid, equilibrium are established because partial ionization occurs, which means there's still that constant, some reionizing and others coming back together. Now, what this means is with ionization of acetic acid, we will form an equilibrium. Okay, so here's our acetic acid or ethanoic acid plus the water. We now get a hydronium ion, and these both have aqueous next to them. So those we get a hydronium ion and our anion. All right, so that's equilibrium of ionization. It's super straightforward. Now let's look at some calculations. All right. Now, basically, the hydrogen ion concentration of a strong acid solution is known. We can work out the pH. We can also go the other way. If we know the pH, we can work out the concentration of the formula, and we do that with these two. Okay, so pH equals minus log 10 of the hydrogen ion concentration. However, the hydrogen ion concentration is 10. It's the inverse log of the pH, of the negative pH. Okay, so I'm actually going to do some calculations in a second, so we'll see how that works. So if the concentration of a strong acid is known, then we can work it out pretty much. But we need to know whether the acid is monoprotic, diprotic, or triprotic. Okay, so hydrochloric acid, for every it's a monoprotic one. So the pH is equal to the concentration of the hydrogen ions is equal to the concentration of the acid itself. Okay, the hydrogen ion in a diprotic, however, is equal to twice the concentration of the acid. So that's for 1 molecule of acid, it gives off 2 molecules of hydrogen ions. Triprotics, for every 1 molecule of acid, they give off 3 hydrogen ions. Okay, so the concentration of the H plus is equal to 3 times that of the hydrogen. 3 times that of the actual molecule itself. All right, so let's have a look at that just to show us. So here we've got hydrochloric acid. It splits off like this. This concentration of hydrogen equals the concentration of that. Here, the concentration of hydrogen is 2 times that. So once we worked out the concentration of hydrogen, or the pH, we could use that to work out the concentration of the hydrogen ions, which would then be twice the amount of sulfuric acid. All right, so we want to work out what is the pH of an acid where the hydrogen concentration is 0.02 moles per liter. Now, if we pop up our calculator, we can do this. We can go 0.02, okay, log plus minus. That's it. It is as simple as that. It is 1 point. Now we went to 2 significant figures, so we would call that 1.7. All right, 1.7. Straightforward, super simple. Now, if we were to go the other way, we then get that number there, so we press equals to shore it up, and we press that. Nope, that's not right. So let's restart that one. Let's see. All right, so we go to 0.02 log 10 to the minus. All right, there we go. Equals that 10 to the minus log, and there's our concentration. Okay, so you're essentially just doing it backwards. Now it's this button here, that's the inverse of our log. Alright, sweet as. That's all super straightforward, and we're going to do some probably more complicated stuff than that in class related to it.